How's it going?
Hi, sorry.
Hey, Sri.
Ben, can't hear you.
There we go. The meeting tomorrow is also at 10 a.m. Eastern.
Yeah. Got it. No, I didn't check my email in the evening. Sorry, my bad.
Okay, looks like let's just get started because, like I said, I have to go like literally at 11.
Yeah, let's start.
Can't, like push that back. So yeah, it would be good if people could arrive on time. So okay, I guess it depends. So I mean, this is supposed to be a pretty informal discussion. It largely depends upon the audience. So I'm not giving really a talk. It's just like, you know, sort of again an informal discussion. So I could start with this discussion of spaces of laws and microstates, but Sri already knows that. I don't know how Roy and Aldo are feeling. Roy, would you like a refresher on this? Roy, I can't hear you.
I said I'm okay. Yeah.
Okay, Aldo, would you like a refresher on this laws and microstate stuff?
No, I'm good.
You're good? Great. Okay. So then I'll just start by talking about what the GUE is. It's the Gaussian Unitary Ensemble. So what this is this is random matrix, so that if I look at its diagonal entries together with square root of 2 times the real part of its off diagonal entries, or super diagonal entries, I guess, and square root 2 times the imaginary part, these are IID with mean 0 and variance 1 over k. So this normalization is important. I'm not going to focus too much on it. You should basically just take it as this normalization is there so that theorems work. And the main theorem, which again is a reminder to most people, but just to set things up, Wojciechowski's asymptotic Freeness theorem. So if I take a k tuple, or R tuple rather, of k by k self-adjoint matrices, and if these are IID and GUE, so each are distributed as above. So again, if you're less familiar with this probabilistic notion, right, I can just think of Mn of C as self-adjoint elements of N of C as like copies of real numbers down the diagonal, and then some copy of R2, you know, on the super diagonal. And basically what I'm saying when I say that they're IID is you take some product measure where each component is Gaussian and it's chosen so that these things work. So then with probability 1, the law of xk, so I didn't do recap of this, but this is what I mean by the law of xk, converges to the law of S, weak star, where S, which is S1, SR are free semicirculars. With mean 0 and variance 1. And again, this just means if I take some normalized trace of these, this converges to the trace of the corresponding polynomial. Okay. And so that's the sort of result that everyone, well, everyone in free probability at least knows, and is sort of the motivation for the whole subject. Again, I think most people are familiar with this, but just as a reminder, you know, what does it mean to be free semicirculars? I mean that like d mu. So if I look at the spectral measure of Sj, it's absolutely continuous with respect to the big measure, and it has density. You know, the semicircular distribution, so just the area under semicircle of radius 2, and S1 through SR are freely independent. Okay, so in particular, this implies that the von Neumann algebra they generate is just L of FR, just the free group factor. Okay, and so the main thing I want to talk about over the next couple of days is this theorem of mine, and I won't state it in. Well, I'll unravel it in a bit. So consider the following. Let's let x and y, x1k to xrk, y1k to yrk, independent GUE. So what I mean is that each of them are should say IID. So each of them are GUE distributed, and they're independent of each other. So again, this you can just think of in measure theoretic terms as saying that I put this probability measure on M, you know, K by K self-adjoint matrices. Should specify that Xij, Yik. These are K by K self-adjoint matrices. So you think of this pair X comma Y, this should really be Xk, Yk. I can do this pair Xk, Yk as living in the 2rth power of K by K self-adjoint matrices. I had this measure that I specified before on K by K self-adjoint matrices. That was the GUE, and I just take a 2R-fold product of it. Okay. Everybody with me? Then for all polynomials in 2R variables, I'll just list the first R of them as T's and the second R as S's. P of X K tensor the identity on K by K matrices. This is the identity of MKC. 1K tensor YK converges in operator norm as the heck K goes to infinity to the same polynomial in S tensor 1 tensor S. So this is the min tensor product. And 2, this is this Peterson-Thom conjecture, I guess now a theorem. So if Q inside of LOFR is amenable, well, let me say it like this. Q1, Q2 set of LFR are amenable and they have diffuse intersection, then the algebra they generate is amenable. So again, I think for people who maybe are less familiar with this, amenable here is just equivalent to saying that Q can be written as some closure of an increasing sequence. Where the QKs are finite dimensional. And this equivalence is due to this deep result, this deep theorem of Kahn from 1976. So again, yeah.
Quick question. Can you tell me what Hagerup-Thorne-Bjornsen's theorem is?
Great. Good question. So reminders. First off, if I have that the law, so let me say, how do I say this? If I take some tuple of K by K self-adjoint matrices and their law converges to some some S tuple. So this converges to the law of A, where A is an else tuple in some tracial von Neumann algebra. And if any polynomial in them converges in norm, I'll say that the law, this assumption here is weak star convergence. I'll say that the laws converge strongly. Okay. Now the Hagerup-Thorne-Bjornsen theorem says that if I take the law of just a single GUE, then that converges to the law of a free semicircular strongly. Okay. So the difference between that and this condition 2, this condition 1 rather, is that so we already know that the law of xk tensor 1 and 1 tensor yk converges to the law of s tensor 1 and 1 tensor s weak star, right? That's just a corollary of Wojciechowski's asymptotic Freeness theorem, which gives convergence of the law for a single tuple, right? But if you have it for one of the sides, the fact that it passes through the tensor product is not a big deal because you can just take, all the polynomials you care about are just sums of elementary tensors, and you just check this on the elementary tensors, and it just sort of makes it trivial. But the strong convergence is really a big deal. Okay, that's really the big thing is the convergence in norm here. It's hard to sort of space this out on the tablet, but this condition is strong convergence. Right. And that's really substantially different. To convince people of that, let me mention that it's really, really, really important that the x's and y's are chosen independently. So if I choose x equals y, this will never be true. Okay. So it's not something where strong convergence is automatically continuous under tensoring like weak star convergence is. If I choose x equals y, then I can just use non-amenability of free group factors to see that.
By strong convergence, do you mean? You mean just this condition, right? It's
strong convergence. This is what this means.
Right.
So I mean weak star convergence plus convergence of norms of polynomials.
Yeah.
Yeah.
Okay, so the only difference between Hagerup-Thorne-Bjornsen's theorem and your theorem is that you're looking at you're somehow amplifying the matrices on the left and right.
Yes. So
And
the only
and you're putting them in commuting positions.
yeah, the only difference between their theorem and Belinschi-Capitane's theorem is that you're putting things on the left and right. So, but maybe let me say something about that. So note xk tensor 1k, 1k tensor xk never converges to s tensor 1, 1 tensor s. And the reason for that is just by non-amenability of free group factor. There are there's some S tuple of unitaries in the von Neumann algebra generated by this, and this von Neumann algebra is isomorphic to the free group factor, so I can just choose them to be the things that correspond to the free group elements. So that 1 over S, sum over J and S, J equals 1 to S, Uj tensor Uj bar is less than 1. And this is Uj star op. So you can think of this as just like I'm looking at the conjugation action of Uj on the course, on L2 of FR, tensor L2 of FR. Okay. So if Uj is, okay, approximated, and we'll get into more later how all this works, but if Uj is approximated by some polynomial in these, and if this polynomial has some sort of universal norm, which is, well, let me just say this, such that this is always less than or equal to 1. So it's possible to do that. I don't want to get too much into why. Then this tensor product would have to be tending to something less than 1, some constant less than 1. But because I'm talking about matrices now, matrices are nuclear, right? So I can have this tensor product not act on MK of C, tensor MK of C, but just act on K by K matrices. And the important thing here is that this is at least what happens when I have this act on 1. Okay, so this is acting on 1 as an element of shot into K. This is K by K matrices with the inner product. Product A with B is 1 over K, trace of B star A. Does anybody want me to recap this? I don't know if everyone was paying attention. So it's really, really important that you choose things independently. Strong convergence is not preserved under taking any tensoring, and there's really a big leap from the Hagerup-Thor-Bjornson result to this Belinschi-Capitane result, which is the statement that 1 is true. So the recent theorem here, Belinschi-Capitane, that 1 is true. So 2 follows. Now, my goal here is to sort of, in the remaining, wow, this took longer than I thought. So I want to leave some time for questions. It looks like we won't get into as much of the setup as I wanted, which is
Ben, sorry to interrupt, but I wanted to put forth an idea.
Yeah.
So we're going to meet today for the rest of the 35 minutes. and then tomorrow for,
Yeah, but I have to stop at like 10:50 so that there are questions. Yes.
okay, so we go for the next 25 minutes, and then tomorrow we go for 1 hour.
Tomorrow I have more time, so tomorrow I can go as long as you want.
Okay. So
But
like,
I don't really have time Friday. I might have some time Monday. So I mean, this is basically it.
okay, so here's what I want to get out of this, and then people can pitch in their ideas. But I want to see the full rigorous proof of your theorem on the top.
Well, that's what I'm trying to get to.
Yeah. So you don't have to go really fast. I mean, we can, if that's the whole thing you can do in the next few meetings, that's fine too.
Well, I'm trying.
Okay.
We'll see.
Yeah.
I mean, I will have to skip a few things, but yeah.
Cool.
Okay. Hopefully by the end of today, I can get to like the essential outline. So the first thing I want to recall is this definition of one-bounded entropy. It's also, I'm trying to go slow because it's hard for me to tell if people are, I mean, this is the problem with virtual discussions is I have no idea if people are actually following or if I've just already lost everybody. It seems that with most virtual discussions, at this point in time, I've already lost everybody.
No, please go slow. I mean, it's good. It's a good thing.
But yeah, I can't tell if anyone is paying attention. Great. So let's recall the definition of one-bounded entropy. M tau is a trace of von Neumann algebra. The R, and I'll choose some R positive, which is bigger than the norm of X. Okay. So I want to talk about Voiculescu's microstate space. These are all the K by K self-adjoint matrices to the R. These are all R tuples. Law. No, this is an open set space of laws. Okay. And more generally, if I have another tuple here, I want to consider gamma R K X in the presence of V. So V here should be some neighborhood, some weak star neighborhood. I. And so these are all R tuples so that there exists an X S tuple so that the law of A and B together is in V. Okay. So if you think of elements of the original microstate space as giving you like parameterizing embeddings into ultraproducts of matrices, this microstate space in the presence parameterizes embeddings into ultraproducts of matrices, which have an of the von Neumann algebra generated by X, so embeddings of the von Neumann algebra generated by X, which have an extension to the embeddings of the von Neumann algebra generated by X and Y.
Ben, do you need X in the presence of Y and not V?
V here because I haven't shrunk the neighborhood yet.
Right, but you still need X in the presence of Y, right?
I do at the end, but right now it doesn't make it. I can't write this because it depends upon V.
Right. So okay, sure.
I mean, if you like to overload notation, I could do this, but that's not necessary.
Yeah.
Already adding in the X is sort of overloading notation, but I also have this distance function on K by K self-adjoint matrices to the R. This is a pseudo metric. So basically like take the direct sum of the normalized Hilbert spin distances and look how close they can get after taking unitary conjugates. This is, for me, norm 2 squared is 1 over k trace. The norm 2 is some matrix C star C to the 1/2. Great.
No, not to the 1/2.
Not the 1/2. Great. And so if I take a subset of R tuples of k by k matrices, I'm going to find k epsilon orb omega norm 2. This will be the minimal cardinality of a subset f and omega, so that for all a and b in omega, sorry, for all a and omega, there exists a b and f, so that this orbital distance from a to b is less than epsilon. So you can just think of it as like I take an epsilon neighborhood of f in this pseudo metric, and it covers all of omega. Okay, so it's just the minimal cardinality of an epsilon dense set with respect to this pseudo metric. Okay. So given x and m to the r self-adjoint, y and m to the s self-adjoint, h epsilon of xy is going to be inf over v, lib sup as k goes to infinity, 1 over k squared log k epsilon orb gamma k x v norm 2. So you just take the exponential growth rate of the minimal number of epsilon dense sets with respect to this orbit distance. Okay. So the inf here is over all weak star neighborhoods of the law of xy. So it's a bit hard to parse at first, but a lot of this is motivated by just sort of other things in entropy theory and various other contexts, right? I want to sort of, make my distance. This would be better if I was wearing glasses, but I'm not. So imagine that I'm wearing glasses and I sort of take them off and I can only see things up to distance epsilon. I can't tell two things apart if they're distance less than epsilon, right? I count how many things I get there. That's some exponential number. You actually expected it to grow faster than this, but okay, for various reasons, I really want to do this so that it's actually an invariant. And I sort of put my glasses better and better. So first I sort of want the laws, the approximates that I'm looking at to get better and better. I want to look at small and smaller neighborhoods of the law of xy. And then I want to make my vision better and better. I want to sup over epsilon positive, this h epsilon. There should be an r here. And so theorem due to myself, well, not really myself, actually.
So which part did you say was because of the to make it an invariant?
So the part that makes it an invariant is normally if I were to take, so how do I, there's a related thing, right, which is the microstate's free entropy dimension.
Mm-hmm.
So I write down the same thing. Well, the free entropy dimension -1. If the von algebra generated by x is diffuse. And I divide by log epsilon.
Yeah.
This makes it not an invariant, at least a priori.
Right. Mm.
So yeah, that's the bad thing. So the fact that this is monotone in epsilon, as epsilon gets smaller, this quantity gets bigger, is 1000% what is behind the proof that it's actually an invariant. Basically, anytime you do that, anytime you write down the same sort of quantity and you make it monotone in epsilon, it's an invariant, like no problem. Okay. But the fact that you're doing this dividing by log epsilon, that makes it not monotone anymore, right? Like the quantity on top, like, gets bigger as epsilon decreases, but so does the quantity on the bottom, and so it's very unclear what happens. So the theorem here is that if the von Neumann algebra generated by X is the von Neumann algebra generated by X prime, and the von Neumann algebra Y is the von Neumann algebra generated by Y prime, and these are all tuples living inside some fixed von Neumann algebra, then the one-bounded entropies are the same. Okay, so I won't go through the proof of that because that would take the entire 2 lectures. You'll just have to take my faith on that. But this allows us to define h of n in the presence of m to be h of xy. If the von Neumann algebra generated by X is n, and the von Neumann algebra generated by Y is m. Okay. And by the above, that's well defined. Now, this right now only works for finitely generated von Neumann algebras, but there's a standard free probability way to get rid of that. I mean, essentially, you let the second variable, you let the algebra increase in the second variable, and you take an inf because that's decreasing in the second variable. That's not too hard to show. And then after that, you let the algebra in the first variable increase, and you take the soup over that because it's increasing in the first variable.
So I mean, if you take a countable dense subset, and you just take the von Neumann algebras generated by like increasing finite subsets, and then you just take h of that in the presence of the whole thing, and then take the soup, it'll be the same thing, right?
Yeah, but also I don't necessarily want to restrict my algebras to be separable. The second variable is allowed to be an ultra power. All right, so let me list some basic properties. I'm again running out of time, but at least I won't have to rehash this the second time around. So let me list some basic properties. So h of m here will be h of m in the presence of itself. Again, this thing in the presence is it's trying to count microstates for n that extend to m. So this thing is less than or equal to 0 if the first coordinate is amenable or equivalently hyperfinite. What you really use is hyperfinite. It's greater than or equal to 0 if m has microstates. So that means that it has these finite dimensional approximations and is minus infinity otherwise. For the importance of this talk, it's this one-bounded entropy is plus infinity on free group factors. It's subadditive under joins, provided that they have diffuse intersection. And it doesn't change upon taking normalizers. Should be true if n is diffuse. Also of interest is that if you take the ultra power in the second variable, it doesn't change. Okay. Okay, so you could just take it as an exercise to use these properties to show that all of these properties together imply that free group factors are prime, that they have no Cartan subalgebras, and that they don't have property gamma. Okay. So, and even not knowing why these are true, if you just take these results as axiomatic, if there is a function which does this, then the free group factors have all these properties. Again, in the interest of at least getting to the main idea here, so that I can expand on this more in the second discussion. Let me not go into details on this, but for those of you who know, which I think is actually basically everyone in the room, I can replace this normalizer with this singular subspace. So these are the vectors.
This is like the cherry on top of the cake.
Yeah. Theorem, so that the NN bimodule generated by psi is disjoint from the corpus. Okay, so it contains the one-sided quasi-normalizers. It contains the WQ normalizers. That's in my paper. I think I've also explained that to most of the people on the call at some point in time. Okay. And so the real theorem here. So let me scroll back up. I want to give this condition 1 a name. So I'll call this. I'll no longer call it a conjecture because it's now claimed to be proven. So I'll call this tensor HT. This is a tensor version of Haggard-Thorpe-Bjornson. And so the theorem that I proved is that tensor HT implies that if Q is a subalgebra of M and it's diffuse and non-amenable, then the one-bounded entropy of Q in the presence of M is positive. Okay. So I don't know, let me call this 1.5 because I called the previous thing 2. This implies the Peterson-Thom conjecture. Why is this? This is just because if if I have two amenable algebras and they have diffuse intersection, then H of Q1 join Q2, presence of M. Well, I have subadditivity under diffuse intersections. And so the joint has to be amenable because otherwise, if it was diffuse and non-amenable, it would have positive one-bounded entropy.
Ben, I have an important question.
Yes.
So I mean, this is like amazing. But if you have a copy of some free product of two von Neumann algebras, let's say L of F and inside L of F2, then is it possible to show, like before this result was known, that there exists an embedding of L of Fn into L of F2 with H in the presence is greater than 0?
Yeah, I think for these finite index inclusions, it should be possible.
Yeah, finite index is fine, but I want, like, I don't want finite index. I want, you're right. Okay, I guess you can find a finite index inclusion of Fn inside F2.
Yeah.
Sri, what's the motivation for this question?
No, I'm just wondering because this result is very powerful. So I'm just wondering if it's possible to recover like the existence of some embedding of any non-amenable, let's say something embeds into LFF2, and can you show that there exists an embedding with positive entropy in the presence? Instead of like, this shows that literally every embedding has.
There exists an embedding because there exists an embedding of Fn and F2 with finite index.
Right. So you're right. That answers my question, but not in a very satisfying way. But it's fine.
Yeah, once you get beyond, like, certainly for very general, non-amenable things, this was not known.
Even the existence of like something.
Yeah, I haven't thought enough about this.
Okay.
Other people here might be more familiar with the Peterson-Thom conjecture, saying that given a diffuse amenable von Neumann algebra, there's a unique maximal amenable extension. This also identifies the maximal amenable von Neumann algebras with the Pinsker algebras. So this would be Q inside of M or P inside of M diffuse. It has one bounded entropy 0. And if I take a proper inclusion, like a proper extension, then I have this. So these are like, because of this theorem, these are exactly the same as maximal amenable things. So it kind of makes sense that this proves Peterson-Thom, because you know, if you're going to say that everything has a unique maximal amenable extension, you kind of have to identify what those extensions are. No, there's a two-step procedure. To the proof.
Ben, one more question. So this result works only for LFF2, right? It doesn't work for.
Works for LFFR.
Yeah, right. It works for LFFR for any R.
Any interpolated free group factor.
Yeah. So it doesn't work for amalgamated free products.
No.
Over amenable.
If you start taking arbitrary free products, I mean, the Peterson-Thom conjecture is not going to be true without.
Right. So if you take arbitrary free products of like strongly solid
Take
things.
von Neumann algebra. Take any von Neumann algebra which doesn't satisfy the Peterson-Thom property.
Sure.
And take its free product with literally anything else.
I know. Yeah, I get what you're saying. But I guess you can. My question would be like, would it be interesting to show some result for like subalgebras that don't intertwine into the left or the right, something like this? Because
I think generalizing this beyond free group factors is going to be very difficult. Just because already they're like obvious counterexamples, and so you somehow, if you want to use this approach using random matrices, you somehow have to do something very different.
But the nice thing is that the nice thing.
1 minute left, so I would.
Oh, right.
You can go ahead and ask, but then this means that I won't state the core idea of how you get. I mean, just go ahead and ask.
I mean, if there's only 1 minute left, I'll just go ahead and ask, and then you can go. You can do this next tomorrow. But there's a nice thing is that if you have a subalgebra of a free product, then there is a trichotomy theorem that says that either it has certain nice structural properties, or it intertwines into one of the sides. So that's why I'm saying that if you don't intertwine into one of the sides, I would suspect that the one bound entropy in the presence has to be bigger than 0.
Right. So this would be like, I don't know. This would possibly be true. It would require. The thing is, I don't know how you would turn that into a random matrix result.
I see.
I mean, it might be possible, but I mean, well, let me state the general procedure, and then stop there, and then I think that will clarify some things. So there's a two-step procedure. If this is, well, it's 0 because I'm taking, it's not less than or equal to 0. It's equal to 0 because I'm taking free group factors. They have microstates. then for almost every tuple, okay. Well, shit, I'm already, okay, yeah. Okay. So I can look at this theta sub x. This is the embedding into ultra products of matrices. I apologize, I didn't have any time to explain what that is. Not really of LFR of the von Neumann algebra generated by S. And it sends a polynomial to the same polynomial in this random matrix. Okay. So if I look at this homomorphism, this embedding restricted to Q, then for almost every choice of X and Y, it's unitarily equivalent to the same homomorphism restricted to Q. In part two, if tensor, so let me say it like this. If I have any collection, AK, BK, and MK of C, self-adjoint to the R squared, so these are two R tuples. And if the law of AK tensor 1K, 1K tensor BK op converges to the law of S tensor 1 tensor S op, then for all Q less than or equal to M non-amenable, sorry, this is strongly, it's a strong convergence. And for every non-amenable subalgebra, if I define this theta as before, like theta A is sort of the, you know, the embedding corresponding to sending S to a polynomial in A, right? So this M here is the von Neumann algebra generated by S. Then these two things are not unitarily equivalent. So theta A here is the embedding to ultra products sends S to this tuple.
Mm-hmm.
So, you know, obviously if you buy these two results, then you're done. Okay.
Wait, 1 second. Right.
So I should stop here and pause for questions, but let me just maybe say one thing, which is that so 2 is not a random matrix result. 2 just literally reads as true. This M doesn't it doesn't really have to be the von Neumann algebra generated by S. You could just take any von Neumann algebra and assume that there exists these microstates, right? So anytime you have strong convergence, you get that for every non-amenable subalgebra, you know, you're not going to have that these choices are intertwining, right? So strong convergence on the tensor product is a very strong result. It says, well, that when in particular, that when I restrict to any non-amenable subalgebra, these two embeddings are not conjugate, right?
Yeah, so
And so this is why I'm a little less optimistic that you can get what you want, where you only get the result for certain non-amenable subalgebras. You would need some sort of relative strong convergence.
no, I think it's possible. I think it's possible. I want to see the proof of this though, and then we can discuss further.
Well, so yeah, things are proceeding a little bit slower than I expected. So I don't know. This is unfortunately, I really have to leave at 11. So I can't push that. I can try to resume this in the afternoon if they haven't dilated my eyes. Or it's an eye exam. So
wait, so you have basically shown that for any subalgebra of L of Fn, there are two for any non-amenable subalgebra, there are two embeddings that are not conjugate by any automorphism. Or have you shown that?
By unitaries.
By unitaries, but that's kind of, yeah, that's the two specific ones are just the left and the right ones.
So yeah, I think I'm not entirely optimistic that we can really get through both parts of this next time. Maybe I'll focus on the second part. Let me say that for something about the first part. This is concentration of measure implies microstates collapse. So this is sort of actually a really general principle that concentration of measure says that all the when you have this nice concentration of measure with respect to the distance in question, in this case being the orbital pseudometric, then all the microstates collapse onto one point if you take something which has one bounded entropy 0 in the presence.
Right.
And this was used also in my paper with David Jekyll, Brent Nelson, and Thomas Sinclair. So you can also read about it there. So maybe what I'll focus on next time is the part 2.
Yeah.
Does that make sense? So the part 2 is doesn't use random matrices at all. So unfortunately, then if I don't get to part 1, then I'm hiding how the random matrices come into play. But the important thing is that the underlying probability distribution for these tuples of matrices is satisfies this exponential concentration of measure with scale k squared. In probability theory, for whatever reason, you call the exponential rate of decay a scale, and the scalar that you multiply to make the appropriate quality true a rate. But I didn't make the terms, so don't ask me.
By the way, so I have a nice remark is that in Jung's proof of like for anything non-amenable, you have two embeddings that are not unitarily conjugate. It's literally exactly like you take some embedding, you amplify it on the left and the right.
Yeah.
And this is like something fundamental that like when you're amplifying on the left and the right, things get complicated.
Well, but his proof is like, so I should mention that you can't, like, obviously part 2 is a generalized Jung result.
Yeah.
It says that a random pair works instead of just there exists a pair which are not unitarily conjugate when restricted to Q. It says that a random pair works.
Yeah.
But you can't, to my knowledge, you cannot adapt Jung's proof to work in this setting. Because
Yeah, of course.
you do what he does and you take something and you put it in block form, that's like a very measure 0 phenomenon.
Of course.
So that's, yeah, so it really is actually sort of different in a way. I'm not sure his construction will ever produce pairs of microstates that don't, that converge strongly in this sense.
Beautiful, very nice. Thank you very much.
Yeah. All right,
I guess
so
we'll meet tomorrow and continue.
I'll meet tomorrow and we'll start with 2.
I mean, if you could explain those 2 steps again tomorrow when you start, or just refresh it.
Yeah,
So
well, again, yeah, I can do that.
So
But
step 1, you're not going to cover step 1 tomorrow, right?
I don't know. I mean, I might be able to. It depends upon how much time we have.
Okay.
But unfortunately, today I had to leave at 11 and the meeting starting late. So yeah.
No problem. Yeah, this is meant to be like not very formal. So I think, yeah.
Well, it's just, I mean, yeah, I can have further meetings about this. They just can't occur. Like, there's maybe a possibility for one more meeting this week, but we might have to do like 2 tomorrow. If we did that, it'd have to be like a last minute thing. I could do something like Monday next week, but then after that, it's going to be, I'm traveling for 3 weeks. So
yeah, Monday is difficult because we're going to be in Waterloo. So.
Yeah, so we'll all already be in Waterloo. That's the only reason I can do it. But
yeah.
But yeah, so I don't know. Maybe it's best to just pause the recording.